Okay. Okay, let's get started. So, for those of you who couldn't make it to the previous lecture, we had a makeup class the Friday before spring break. It was lightly attended for the in-class section, so be sure to go and look at the video recording. Okay. We are actually going to continue. So, in that class, I talked about time ordering, clock synchronization, I talked about GPS, and I started some initial discussion on this notion of logical clocks. Okay. Some of that material is directly relevant to what you are going to be implementing in lab number 2. So, you need to be familiar with it. Okay. If you have any questions, you can always come and ask during office hours or on piazza. So, what we will do today is continue the discussion. So, we are going to focus our attention on logical clocks, which I had briefly introduced last time, but since it's been a week of spring break, I'm going to do a quick refresher on it and then discuss how to implement logical clocks. We'll discuss this notion of vector clocks, and we'll start talking about distributed snapshots. Okay, so the rest of the material, which is termination detection, leader election, distributed locks, we will defer to next class because we won't be able to cover all of that material. Okay, so let's start with logical clocks. Okay, so this was a slide from last time, so I'm just going to do a quick recap. So what I said is, in many scenarios in a distributed system, you want to essentially timestamp events to reason about the ordering of events. You want to know if event A has actually taken place before event B. Okay. So timestamps are used to compare and reason about the ordering. The actual time at which event might have occurred may not be as important. Okay, that's not universally true. In some cases, whether an event has occurred at a certain time t. In that case, timestamping that event with the actual time and trying to reason about when that event occurred is important. But if you're simply comparing two events and you want to know which event has occurred before which other event, or you want to have one event trigger another event and so on, then you just need to understand the ordering of event. The absolute time in that case is less important. So for those subset of scenarios where we don't care about the absolute time at which events are occurring, okay, an event could be anything that you care about in a distributed system. It could be sending a message or anything that actually you care about. So we are going to use this notion of a logical clock to compare the ordering of events. Okay, and we will do away with the notion of physical clocks. Okay, so in this case, we no longer will need clock synchronization. We will not use the actual clock that is on your machine that can tell you the time. Okay, we are going to use this notion of a logical clock, which is simply an integer. Okay, and here are essentially the ideas. Okay, so if two machines do not communicate with one another, then we assume that they are not part of the same distributed system. Okay, so we don't really need to care about synchronizing them or reasoning about what's happening on those two. Okay, essentially in a distributed system, there has to be some communication. So if two machines are never going to interact at all, they are not going to be part of the same application or same system, so we don't really worry about them. Okay? Only machines that communicate with respect to one another for any task are the ones we care about, and on those machines, processes will need to agree on the order in which some events are occurring and not necessarily the time. Okay? If you care about time, then you cannot use logical clock. That goes without saying. So essentially what we want to do is define an event ordering, which is we want to define a total ordering of all the events that are occurring across all of the machines. So if there are n machines and each is seeing some subset of the events, we want to construct a global order, okay, which is if you have a timeline, you will have to say which order these events have occurred. Okay, so that's what we will call event ordering. And the way we are going to do this is using this notion of a logical clocks, but there are some assumptions we are going to make here. Okay. So first assumption is, on a single machine, you can always order events. Okay. Events occur in program execution order. Okay. So if a sequential program is executing, okay, let's say we are just looking at events of what statements are being printed by that program on the screen. So if it executes some print message and some message arrives, and then it continues execution and executes another print message, you know the order in which those events are occurred. Okay, that's essentially in program execution order. Okay, so program execution, because it's sequential, gives us a natural ordering of events that are occurring within a process. Okay. Even across processes on the same machine, it is straightforward to actually order events, because you can simply take the time of the event, okay, based on local clock, and simply order all the events according to time. Only across machines when there is a problem, because unless your clocks are synchronized, you cannot use timestamps to order events. Okay, actual physical timestamps to order event. But on a single machine, either you will use program execution order, or you are going to use timestamp to order machines, to order events on the machine. Okay, so events in a single processor machine will assume are totally ordered. Okay, in a distributed system, we will assume that there is no global clock. Okay, I introduced this notion of what's a global clock. Global clock essentially says perfectly synchronized clocks on all machines. Okay. No such thing exists, because even with any clock synchronization, okay, we talked about NTP and things like that last time. Okay, even with any clock synchronization, there is going to be some error. Okay, so we cannot assume there is going to be a perfect clock, and in this case, we do not even need such a clock. Okay, so there is no global clock. We will assume that local clocks can be arbitrarily out of sync with respect to one another, because we are not going to use physical timestamps. We don't really care, okay, about them being synchronized. Okay. But we need to find an ordering of events across machines. On a given machine, you know what has happened, but then how do you do this across machines? And the key idea came from Leslie Lamport, which is going to be the basis for logical clocks. They are also called Lamport's clocks. Okay, last time I also mentioned that Leslie Lamport is a famous computer scientist, designed many techniques in distributed systems. Also, he is the designer of LaTeX. LaTeX stands for Lamport's tech. So this is the first time we are encountering one of his techniques. We'll encounter several more. Okay. So the basic idea is, if processes are going to exchange messages, we can use message exchange to naturally order events across processes. Okay. And the simple idea is, if every message that's going to have two events associated with it, the sending of the message and the receipt of the message. Those are the two events. Okay. There's a natural order between those two events. A message cannot be received before it's sent. Okay, that's an obvious thing. So we are going to essentially use send and receive events of messages to order events across processes. Okay, and I drew a picture last time, which I'm going to redraw here, which will give you the idea of what we are talking about. So here is process A. Let's say there are some events. This is timeline. Okay, that's process on machine 1. Here's this process. There are some other events. Now let's assume that this is the send, that's the receipt. Okay, that's a send, that's the receipt. So on a single machine, single process, we know this is the order of events. On this machine, you know that's the order. We cannot directly compare the order across machines as of now. But now, given that the send has to have happened before the receipt, okay, and send and receipt are now events on two different machines. Okay, you can find an order. Okay, essentially, all of the events, okay, that precede the send have happened before the send, okay, because they are local events. Okay. All of the events on process B that happen after the receipt are also ordered, okay, because that's also local order. Okay. Now we are just going to use the transitive property. Okay, if these events have happened before the send has happened before the receive, and the receive has happened before those events, you can take these events on process B and these events on process A and find an ordering. You can say which of those have happened before which others. Okay. So without using any timestamp, any clock synchronization, just by a single process message that has been sent from one machine to another, we have actually ordered events that have occurred on that machine prior to the send, and all events that occur on the receiving machine after the receive. Is that clear? This is what I explained last time. I'm just repeating it for those of you who may have missed it. Yes, question.
So what, I'm sure there's different algorithms for the number of messages to receive and stuff like that, but on average, how many events go unordered because they don't fall on the right side of, like,
okay, question is how many events that can be unordered. So for that, let me explain what unordered messages mean. So the process, all the events before the send here and all the events before the receive here cannot be ordered. Okay, all we can say is this timeline is the ordering that we have derived. These set of events before the receipt and those set after the send cannot be ordered with respect to one another. Those are unordered events as of now. If there are additional message exchange, maybe we can find additional ordering. Okay, but with single message exchange, that's all we can do. It's partial ordering that we've derived, not a total ordering. Okay, and the question that is being asked is how many events remain partially ordered. That depends on the frequency of message exchange. Clearly, there is no right answer for that. It depends on how many events occur and how frequently messages are exchanged on machines.
What's an acceptable percentage that's used in like industry?
What is an acceptable percentage that's used in industry? So I should mention that we will talk about logical clocks. By default, most tech applications end up using physical clocks. They will assume clock synchronization, they'll use real timestamps, and they'll order those events. There are fewer applications that actually use the notion of logical clocks, even though it's powerful. Okay. Another way to answer that question is, if you are writing a commercial application, you might just say, let me use the local clock, timestamp it, and assume that clock synchronization is accurate and deal with it later on. Okay, but as we talked about last time, there are errors in clock synchronization, so that's always a risky move. Okay, any other questions here? Okay, so this is basically what we are going to use now, and we need a technique that will allow us to assign logical timestamps to those events to derive that event ordering. Okay, and so the next step for us is to actually define the happened before relationship formally, and then explain what the logical clock algorithm is actually going to do. Okay, this relationship is very simple. It says if A and B are events in the same process, okay, it's just one process that's executing events, and A and B are events on that process. If A has executed before B, okay, that's program execution order. We are going to say A happened before B. That arrow thing is called happen before relationship. Okay, that's obvious. Okay, if A represents the sending of the message, B represents the receipt of the message, then A has happened before B. Send has to have happened before receive. You cannot receive the message before it's even been sent. Okay, so send and receive of a single message already ordered. Okay, and the third thing we are going to say is relationship is transitive. If A, B, C are three arbitrary events of any sort, and you know that A has happened before B and B has happened before C, if that's given to you, you can then say A has happened before C. Okay, so relationship is transitive, which is the same thing we did here. We could derive an ordering of event before the send and after the receive because of transitivity. Okay, because we simply knew that send has happened before the receipt, we could order these and those, and that way you could get a partial order. Okay, that's what happened before relationship. Okay, and it also says it's undefined across processes that do not exchange messages, or if there's message exchange, anything after the send or before the receive cannot be ordered. So it's a partial ordering that we get, not a total ordering. Okay, that's just the definition of happened before. It doesn't tell us how to do anything yet. Okay, so now here is our logical clock algorithm. Okay, here the goal is stated at the top. It says if A has happened before B, okay, we want to have a technique that's going to assign clock timestamps such that the clock value of A is less than clock value of B. So A has happened before B, we want a timestamp of event A to be less than timestamp of event B. These are going to be logical timestamp, not real clock values. Okay, we'll define this notion of a logical clock, which is simply going to be an integer. Okay, so essentially you'll timestamp events with some integer values, and if A has happened before B, we want that the timestamp that you assign to A has to be less than the timestamp you assign to B. Okay, yes.
What if events are happening faster?
What if events are happening at a frequency faster? Because you can always tick for example. Yes, so granularity of or it could be some event such as an interrupt, a packet arrived on your network interface card which will give you an interrupt. Okay, you can certainly order those or timestamp those. Order those. You can timestamp those. Okay.
Would we wait a lot of cycles just like iterating our integer or something like that?
Okay, question. Don't you waste CPU cycles iterating integer? So this is no different from timestamps. If we are not going to say, you define what they could be sending, receiving messages, they could be something interesting happening. In the lab one, it time your nothing else. So you will not do this for every instruction or anything like that. So it is not going to be that expensive as a result. Okay. All right. So if A and B are concurrent event, we don't care about the timestamps. Okay, only care in this case if A has happened before B, we want that ordering. If they are concurrent, we will let the timestamps be whatever they are. Okay. So here is how it's going to work. Okay, we will assign to every process an integer, which is going to be our logical clock. Okay, every time a local event occurs, that process will take the integer value. Okay, local event is, or any event is defined by the application designer. What do you care about? You can define in your lab, for example, what events you cared about. Update to sports score, receiving a client request. Those are maybe events you care about. Okay? So every time such an event occurs, you are on a local machine, you are going to increment your clock by 1. Okay? So basically every machine maintains a logical clock. Whenever there's an event, local event, increment by 1. Okay? When you, yes, question. What about overflows? We'll assume it's a long enough integer that we don't care. This is an abstract algorithm. Okay, in abstract, integers don't overflow. Okay, in theory they do. All right, so let's not worry about that for a moment. Okay, but to be more serious about your question, you have to define a clock value so that outlines the lifetime of the process. Okay, the number of events cannot actually exceed the number of bits you have in that clock. So that's how you have to define it. But in this case, it's just an abstract algorithm, so we don't worry about implementation details as of now. Okay? So here is what now you have to do that's interesting. Whenever you send a message, okay, you want to basically take the local value of the sender and piggyback it with the message. Okay? So the message will actually have actual message content, but in addition to that, you are going to send the local clock value. Okay? So in this case, when A sent a message, I'm going to erase this just to make it clear. Okay, so your process A is B. Okay, that's your message. That's the send receive. So in addition to the message, you are going to actually include the clock value of this event. Okay, so here, let's say, so that was send was event number 4. You are going to actually send 4 on the message. Okay, with the message. Okay, when you receive the message, what you are going to do, you are going to take your clock value, the clock value of the what came with the message, take the max of the 2. Okay, and then assign that event to be the max of the 2 clock values plus 1. Okay, so essentially in this case, let's say this was event 1, this was event 2. So the receive would have been event 3 had it been a local event. Okay, so essentially here what you are going to do is max of 3, 4, which is the thing that has come plus 1. Okay, so that's going to get actually 5. What you want, because if this is 4, this cannot be less than 4, because these two events are ordered by happened before, and this has to have a lower timestamp than that. Okay, that is why doing the max of the 2 always ensures that you will assign it the bigger of the 2 timestamp. Okay, and that's it. So every time you have a local event, you are going to piggyback the local clock value when you receive the message to take the best clock, local clock, the one that came from the sender, max of the 2 plus 1. Okay, yes, question. What's the question now? Max 2 plus 4, you could do that as well, it doesn't matter. Okay, I'm just giving the simple, I assume that you take the clock, actually you could do 2 plus 4. Okay, I assume you take and then you add, then you don't need to add 1, you're actually right. So you'll take the local clock, which is 2, 4 plus 1. Okay, that's what you should do. Okay. So there is a picture. So this, I'm going to show you an example. This came from the book. Okay, so this is actually a picture from the book. So here is 3 processes, P1, P2, P3. You will see that there are some clock values shown. There is some arbitrary message exchange. Okay, this picture, which is on the left side, does not use Lamport's clock. So you will see that often there is a send, and the message send has local clock value 60 on P3. When it is received, this clock has only advanced to 56. Okay, this clearly violates our goal, because we said that if two events are ordered by happened before, you want the clock values to also be in that order. Okay, so now if I give you 56 and 60 and ask you which event happened before which other event, you cannot actually reason the right ordering, because clearly the send has happened before the receive, yet receive's timestamp is lower. This is because you didn't use Lamport's clock. Okay. If you had used Lamport's clock, this is what you would have done, which is you would have actually taken the max of whatever that is, 56 and 60, which came from here, and then added 1, which is why that became 61. Okay. Now you actually, so the clock on P2 has jumped from 56 to 61 just to ensure that the happened before relationship is maintained. Okay. Is that clear? And the same thing has happened for this other message here, where this went to 60 and then it updated that to 70. You will see that again here, that would have violated our condition. Is that clear? Okay, so there is a simple intuitive proof you can think about as to why this technique is going to give us this property. If A has happened before B, then the clock value is because for local events you are going to increment it, so that's obviously true. And across machines is because of the happened before a relationship is maintained by the sending and the receiving, you get that through the transitive property. Okay, I won't go into the proof, but that's the reasoning.
This is a partial ordering, right?
Yes.
So if you take up randomly one event from process 1 and another event from process 2, you can still not tell which is like the right one. So
Yes.
effectively, what's the use of doing this?
Yes, good question. So question is, we will address that in just a minute, but let me repeat the question. It's going to be a big question. Since you asked it, I'm going to repeat it, but I'll answer it rather than asking all of you to think about it. So the question is as follows. Okay, so there are actually two questions. First is, it is a partial ordering. Okay, so just because it's partial ordering, some of the clock timestamps are not comparable. Okay, in reality is not comparable, yet we have integers. So if I give you, here is the event 60 on this machine, and I say here is event 56. Okay, well that's a bad idea because that's comparable. Let's take these two. Here is 48 and 56, and I say compare those, which happened before which. Just looking at the timestamp, you can't tell. Okay, it looks like 56 must have happened after, but if you look at the picture, it's not the case. Okay, that's a clear counter example saying you shouldn't just use the timestamp and reason, because you can, this is a partial ordering. When events are not comparable, the timestamps are arbitrary. So just comparing them does not tell you anything. Is that clear? Okay. Only if you are told that event A has happened before event B, the algorithm is guaranteeing that the timestamps are in that order. But given two timestamps, if I ask you to reason about how events were occurred, that you cannot do yet. Okay, we will address that in just a moment. Is that clear? So Lamport's clock has this deficiency, which is you can timestamp events in the order, but you cannot reason about event on the timestamp. You also want the opposite to be true. Okay, that was the question. We'll see how to fix that. Okay, is that clear what I said? Okay. Okay. So there are two ways we are going to fix this problem. Okay. One is we are going to say there are partial ordered events, some events you cannot reason about. We will arbitrarily impose an ordering even though there may not be anything corresponding to reality. And that is what is shown in the picture. So what we are going to do is essentially append the process ID. We'll assume that processes are ordered 1 through n. Okay. Each process has its own clock, which is a separate integer. Okay. We are now going to make our clock a decimal value, which is the logical clock value dot the process ID. Okay. So this is process 1, this is process 2, this is process 3. So all clock values here will actually have a suffix dot process ID. So this becomes 1.3. Even though the clock value is 1, okay, you essentially put a dot and put the process ID. Okay, and so on and so forth. Okay. Now because you are using Lamport's clock, whenever the happened before relationship is true, you are automatically going to get the old property, because you are going to at least have any events that are ordered by happened before to be greater than 1 or more, because you are doing the max of the clock values. Okay. Now, when there are arbitrary events, we are simply going to use decimal notation to order them arbitrarily. So, here is event 1 on process 1, event 1 on process 2. Okay, because this became 1.1 and that became 1.2, we just enforced an rule saying that's the order I am going to assume. That may have nothing to do with reality. Okay, those are concurrent events. You cannot actually order them in any one way, but we'll just define an arbitrary tiebreaker rule saying process ID wins. Okay, higher order process will be, so if you have same clock value, higher order process will get the timestamp that will indicate it's happened after, even if it's not really what is happening. Okay. So you took a partial order and now you can order every event because you are already using Lamport's clock, and anything that's not comparable you use decimal values to break the ties. Okay, your question?
So where exactly would we use this? In the sense that if you're using all of this like retrospectively, where you can see then maybe you can like automatically but then if you were to use it like at the moment, then maybe you can't really.
Question is where exactly would we use it? We do want to start reasoning about things. Okay. Now that we have given a total order, okay, this is basically going to be the order which we'll assume has actually happened. Okay. Essentially what you have done is whenever there is a send and receive, that order is respected in this ordering. All this concurrent event, we just said here is a way we will order it because we don't know. And nobody knows because they can communicate. So there's no real ordering you can define on them. We can impose an ordering. Okay. So in this case, you will essentially say 1.1, 1.2, 1.3, that's order. 2.1, 3.1, 3 or 2, 2.1, 2.3, 3.1. So you will just take these values and just sort them, and that's the order. Okay. That's what we are going to assume. Okay. That's not the real order actually, but that's just a way we fake the ordering. It's one way to do it. Okay, we'll see a better way to do it in just a moment. You have a question?
Given any two events on, you can actually find out if they are linked by any communication, right?
Given any two events, can you find out they're linked by communication? Yes, you can log messages.
So that way you can actually reason about their order. Only in the other case is when you assume.
That is exactly right. We are basically building on Lamport's clock. Okay, this is not changing anything. So if you removed all the decimal notation, it will be the same picture. It's a simplified version of this picture here. Okay, so you are running Lamport's clock, but all you are doing is, in this case, if there are, let's say, there are 3 0 events there. Okay, because by definition you can't do anything. You are going to say that 0.1, 0.2, 0.3, and I'm going to assume that's the order, even though that's not a real order. I just impose that as an ordering on the system. That's all. Okay, you've essentially appended a decimal value of the process ID to each of those clocks. That is what is shown here. Okay, and that gives us an actual a total order, even though there are some of the concurrent events which is enforce some order. Is that clear? Okay. Now, having said this, the total ordering still does not tell us the actual order in which events occurred. We just allowed us ourselves to order the events. But if I said 2.1 and 3.2, which event has happened before which other event? You can't say 3.2 is greater, numerically greater, and hence there's an ordering, because Lamport's clock only gives us partial ordering. Okay, we just enforce some ordering, doesn't mean that's the actual ordering. There was a question somewhere here. Yes. Okay.
Just to clarify, once the M1 message is sent, do we the logical clock, does it only count the number of events happened, or can we actually can it actually like measure the in terms of normal physical clock and increment the logical clock according to that?
So the logical clocks do not use any notion of physical clock. They only tick when events occur. Okay. Physical clock is always going to advance. That's a given. Okay. Program execution order is also order of time, because if one instruction executes on the CPU, then another instruction executes, the second instruction has to have executed after the first, because that's the order of execution. Okay, so program execution beyond that, we are not using physical clocks. We are simply using those properties to order whatever events we care about. Okay. Any other questions? Yes.
But even if you only use like Lamport's clock and you could like look at the whole time series, like the whole set of events,
Okay. Question is, if I gave you a timeline picture of this sort and asked you to figure out what order events occurred, could you not do this? And yes, you could. Okay, but in reality, what you are going to have is a program which has basically just put timestamps and put log messages in. You're being asked to say which of these events has occurred before which other event. Okay, this is how you are going to debug your lab. Okay, you are going to send some messages and figure out what happened, why did it not occur. This you will have to actually use some notion of this message was sent, it never got there, maybe something went wrong with the network configuration. So to do various tasks, including debugging programs and so on, you have to figure out the order. Okay, you don't have the benefit of a timeline. Okay. So you want the opposite, which is you want to look at timestamps and reason, not the opposite. Given a picture of this sort, yes, you can obviously reason it. You don't need an algorithm to tell you this. You're just going to look at send, receive, and order things. Okay. So in reality, you don't have the picture, but that's just to explain how things work. Okay. So I'm going to come back to totally ordered multicasting in just a moment. That's something you have to implement in lab 2. But before that, I'm going to go and talk about way to fix whatever problem we have in Lamport's clock, okay, which is in Lamport's clock, if we are given two clock values, okay, you can't compare them and say anything about the order, okay, because there are all these partially ordered events that don't tell you anything. So what you want really is an ability to have a clock algorithm that goes both ways. If A has happened for B, you want the clock value of A to be less than clock value of B. Also, if clock value of A is less than clock value of B, just comparing those timestamps should guarantee us that event A occurred before event B, because that's what you really want. You want to be able to compare timestamps. So we want a technique that will come up with timestamps so that the timestamps are comparable and that comparison is meaningful, that tells you the order of events. Is that clear what we are trying to do? So we want to improve logical clocks and have the implication go both ways. So that's what is said here. In Lamport's clock, if A has happened before B, C of A is less than C of B. But the reverse is not true. You cannot say anything by comparing timestamps. And the question is, if C of A is less than C of B, can we actually say that A has happened before B? Can we improve Lamport's clock to give us the reverse property as well? Okay. So now we will generalize Lamport's clock into this notion of a vector clock that's going to enable direct comparison. Okay. If A clock value of event A is less than clock value of event B, you will be guaranteed that event A has actually happened before event B. Okay. So this notion, okay, is also related to what is called causality in distributed system. Okay. Causality is this notion of time. So essentially, it says A has happened before B, A is causally related to B in time order. Okay. So, and this causality is used in many different scenarios. Okay. We will encounter it in the near future when we start talking about causal delivery, which says if two messages are sent from two different machines, and if send of one message has preceded the send of another message using the happened before relationship, can they also be delivered in that order? Okay. Typically, things like TCP/IP sockets enforce FIFO delivery for a single machine. Okay. If two machines are sending you messages, you cannot order messages that are coming from two independent machines. But if they are actually ordered by the send happened before relationship, then you can deliver them in that. So you can enforce properties of that sort, which we will get to. Okay. We don't know how to do that yet, but we will actually be able to do that by implementing. Okay. So essentially, you need a timestamping mechanisms that says if timestamp of A is less than timestamp of B, A should have causally preceded B or A has happened before B. Okay, so how do we do that? Okay, so here is the algorithm, but I'm going to draw a picture to show you how it works, because that's going to be all self-explanatory once you have a picture. Okay, so we'll take the same example. Okay. We'll do two processes, but it works for n processes. Okay, so now rather than maintaining one integer, every mesh process is going to maintain a vector of integers. Okay, one integer per process. Okay, if you have n processes in your system, your clock is going to have n integers in it. Okay. So essentially there are two processes here, so our clock will have two integers. Okay, so clock is a tuple, so we are going to start with 0, 0, 0, 0. Okay, the ith entry of the integer is the local clock of process I, the Lamport's clock of process I. Okay, so this, let's just call this process. This is process 1, process 2. Okay, so this entry is the local value of A. The second entry is the local value of B. Okay, like before, when there are local events, you are going to pick the vector clock, but your entry in the vector clock, ith entry for process I. Okay, so if there's an event here, okay, on process A, okay, this clock value is going to become 1, 0. Okay, another event, the clock value is going to become 2, 0. Okay, so you're just generalizing whatever we did. So here you're going to get 0, 1, 0, 2, and so on. Okay, now when you have a send, you are going to do the same thing. You are essentially going to send the vector clock in this case. Okay, so let's assume you have a send event 0. Okay, so you are going to send a vector clock 0. Okay. Now when you receive, you are going to do max of the two vectors, which is you are going to compare each entry and set the max. Okay, and you are also going to take your local value by 1. Okay, so what should be the clock value here? Okay, 3, 3. First you do max of the two vectors, so that's going to give 3, 0 as max is 3, and this is 2. So max of the two vectors is 3, 2. Then you will your local clock, which is the second entry. So this is going to get, okay, and then this will continue. So this will become 3, 4, and so on. And here you are going to get 4, 0, so on and so forth. Okay, that's our algorithm. Okay, now the claim is now you can compare timestamps and reason about event ordering. Okay, you should realize that whatever we did previously is still the case. Okay, because the send preceded the receive, event ordering is actually still respected. So if I take an arbitrary event, let's say this one and this one, so I say here's a vector is 1, 0, here's a vector 3, 4, and you will know that this event has happened before this, so you'll see this timestamp is lower than that times. That's still the case. Okay, but furthermore, now we can say that I just tell you the clock values, you compare them. If you see that one is greater than the other, you are guaranteed that that event has actually occurred before the other event. Why is that true in this case?
Because you maintain track of all other processes at each moment.
Okay, you maintain information about other processes. Okay, that's true. But why does it give us this property? Why is the reverse true? It says that if you compare the clock values and one vector is greater than the other, now there is a guarantee. In the previous case, if I told you 52 and 64, you can't say that the event with 64 has actually happened after. You can't say that. In this case, you can. Okay? To understand that, you have to understand what happens to concurrent events that do not have a relationship. Okay, let's take some events of that. So let's take 1, 0 and 0, 2. Okay, you will know that these two events are concurrent. There is no ordering because there is no send or receive. Okay, now you compare them. Okay, which vector is actually greater than the other vector? 1, 0 is greater. 1, 0 is less than 0, 2. You should say what is the definition of less than, first thing. Okay, so definition of less than is the following. Okay, if vector I is less than vector j, okay, strictly less than, let's say v of I is less than v of j, that means every element of I has to be less than every element of j, strictly less than. There has to be at least one element here that's strictly greater than that element. That's our definition of less than. Okay. Now, if you compare them, can you order them by less than? Okay. So, you will see that in this case, one element here is greater than the other one, but one is less than the other one. So, those two vectors are not comparable by definition of the less than relationship. Okay. Since they are not comparable by definition of the less than relationship, you cannot say anything about their event ordering. Okay. All we said is if V of A is less than V of B, you are actually guaranteed that there has happened before relationship before those events. Because every concurrent event will have vector values that are not comparable by definition. Some values will be less in the vector, others will be more. So those vectors become not comparable. So you say we can't order those two events. Okay. We didn't say you are going to get a simply said that if V value of A is less than vector value of B, then A has happened before B. That we get here because the Lamport's clock value is still maintained. Okay. Whenever there are concurrent events, and the same is true here. See what has happened before the sends. This is 0, 2, that's 4, 0. Again, they are not comparable. Every time there is a sending and receiving of a message, all of the events before the send and all of the events after the receive get automatically ordered because here you do a max. Okay. If this is the max of the two, all of those events have to be strictly less than that max. Okay, they automatically get ordered, and everything after the receive, you will actually increment the local value. So all of this will be strictly greater than that. So you got your ordering. Okay, is this clear? So essentially, vector clocks will now allow us to do the opposite reasoning as well. Okay, you will assign by simply using integers and message exchange. You now gotten a nice property which says I can compare timestamps. There is no clock synchronization involved here. Okay, your clocks can be arbitrarily out of sync. You don't care because your clocks are essentially integer values that you tick when events occur, events you care about occur. Okay, yes.
In some sense, isn't this
In some sense, the converse not important. Yes, in most cases, if you want to reason about timestamps, you will want the converse. Okay, Lamport's clock don't give you the converse, which is why they generalized it to give vector clocks.
so why is that helpful?
Why is Lamport's clock helpful? Lamport's clock can still be used if you actually don't want to reason about events, which was the way I just explained. Allow ordering. It happened before, but it just arbitrarily merges concurrent events and imposes some arbitrary order. Okay. So if you want to order those events, you care about. So here is that's why I'm going to go back. I skipped a slide. Okay. So here is a simple example of why you might want to care about ordering, even though you want to derive an order and have everyone respect that order. Okay, the example is that of a banking database. Okay, so it's a more real world example, not abstract processes. Okay, so we assume that there is a bank, okay, and the bank has a database where it maintains its account. Okay, and then you have replicated that database in two locations. Okay, this is done for disaster recovery, fault tolerance. If one database fails or there is a disaster, you don't lose all your data. There is a copy somewhere else. Okay. So a lot of important applications are going to replicate the data. So this is essentially replica 1, that's bank database replica 2. Okay. Every account is replicated in both of those locations. Okay. Now we'll assume that there are two users, okay, that are making updates on their accounts, or maybe on the same account, it doesn't matter. Okay, so essentially user 1 might go and say, I am going to take some money out or transfer some money from one user to another, or the user 2 could actually be a process that's updating, maybe adding interest to your monthly balance or some such thing. Okay. Now, because these are replicated databases, the queries that the users make to update the database have to be sent to both the replicas. Okay. If this user says, I'm going to withdraw $100 from the ATM, okay, you have to send a query to replica 1 and a query to replica 2 saying deduct $100 from the bank balance, so that the account is synced in both places. Okay. And same thing here, which is why you see that any request that user makes is sent to both replicas. Okay. That user is also going to send request to both the replicas. Okay. Now it is important from a consistency perspective that all the updates that are being made to the database, both replicas are actually made in the same order. Now, as you will see in this picture, you will see that this user is closer to this database than that database. So, if you issue the query, okay, the query is going to hit because the latency to this replica is lower. That may be a far off machine. Your query will arrive here first, and query may take an extra tens of milliseconds before it arrives here. Okay? And in this case, that user is actually closer to this machine, the replica, than the other. So, his or her queries will hit this database replica first and that database replica later. Okay? If they so happen to issue the query more or less at the same time, okay, you might have a situation where users 1 query arrives here first before users 2 query, and the opposite is true here. Users 2 query arrives before user 1. Okay? Often, if user 1 and 2 are unrelated, performing the query in those 2 different orders will have no impact. Okay? If each user is deducting $100 from their bank balance and they don't do anything to other people's bank balance, what does it matter? Okay, you will in the end, regardless of what order you execute them, you will have the same end result. Okay? But that's not true if the users are actually making updates that actually modify related records. So, for example, if this user is actually a program that goes and updates the interest on your bank balance, and that user is actually making a deposit to the bank balance. Okay? If the query is executed in opposite, you will have inconsistency, because if you have $100, let's say you get 1% interest. Okay, here your bank balance will actually get updated to 101, and then you add, let's say, $10 of deposit. So, you are left with 111. If you do the opposite here, okay, you will essentially first get 110 balance and then you add interest to that. Okay, you will end up with a different result. Now, your account's balance is out of sync. Okay? So, it's very important that all of these queries, even though they may arrive slightly at different times, you have to execute them in the same order, not execute them as soon as they come. Okay? So, what that means is it doesn't matter what order you import, you pick an order, okay? But all replicas have to essentially respect that order and execute the queries in that order. Okay? Because in reality, those 2 queries are concurrent. These 2 users are not talking to one another, sending any messages between themselves to impose any order. They are just issuing queries. Okay? And we just want an order. We want which are receive the queries. Okay, that's the order we agreed to execute the queries. Is that clear? Okay. So, this is where you can now use our total ordering idea, because this also gave us a total order. For concurrent event, we just imposed an arbitrary order. So, if all processes can agree that's the order, then our problem is solved. We are going to execute the order of timestamps that we are assigned to them. Clear? Okay, so now how to do this is as an algorithm to do totally ordered multicast. Okay? We have suggested that that's the same algorithm you use for your lab 2. Okay, because in lab 2 you are going to get requests from arbitrary clients and their replication. So, you might get requests out of order at 2 replicas. Decide on a total ordering. Okay, because you said every 100th user gets a raffled entry. Okay, if you have different 100th user on 2 different machines, then you are out of sync. So, you want to agree on something. Okay. So, that's the question is how do you do this? So, here's the technique. So, we are essentially going to use Lamport's clock. We are going to assign these process IDs as a suffix to Lamport's clock. Okay. That's already going to give us the ordering. What it does not do is it does not tell us that as soon as you get a query that there's another query coming, so you better don't execute it, essentially wait for another query to arrive, then execute them. All we know is timestamps. So, what rather totally ordered multicast technique does is it has some additional message exchange to figure out what the total ordering is. And here is how it actually works. Okay, when you send the request, you are going to give it a timestamp, just as you did in Lamport's logical timestamp. Okay. Every message in this case is multicast, okay, which is what we do. Every replica receives every query. Okay, so, all transactions go to both replicas of the database. Okay, so, that's what it means. Every message is multicast. Okay. So, when a message is received, we are going to put it in a local queue. is going to be ordered by timestamps, and you have to send acknowledgements to all other processes, and I received such and such message. Okay, if I receive message 5.2, you send an ACK to everyone else saying I have received message 5.2. Okay, and then essentially you are going to only process messages when the following conditions are satisfied. First is that has to be the message at the head of the queue. Okay, you cannot jump messages, so you always take, you ordered the messages in your buffer by timestamp order, that Lamport's timestamp. Okay, you can only take the message at the head of the queue, and furthermore that message at the head of the queue has to be acknowledged by all the processes. If you received ACK everyone, and you are at the head of the queue, you are ready to go. You can take that transaction and execute. Okay, and here is where you will actually hold things up. Okay, so you can only send an acknowledgement to another process if you have no outstanding request, and furthermore your update has been processed by process I, and your ID is greater than that of process J. Okay, what does this mean? Essentially what this says is, if you are receiving concurrent messages, okay, you cannot, if you have an outstanding message, let's say you are 1.1, okay, and you receive query 1.2, you are not going to acknowledge 1.2 until you have yourself processed 1.1, because you know that you have a query before another query, and you are going to wait for everyone to acknowledge that. Then you process that, only then you send. So you hold the acknowledgement to 1.2 because you know that you have a query that has to be executed strictly before, because that's the ordering that you imposed. Okay, so essentially if you have an outstanding request, okay, so put that in more simpler terms, if you have an outstanding request, you will not send any acknowledgement until your request has actually been acknowledged by everyone else, okay, and processed. An outstanding request essentially says query that has the least timestamp and that was issued by you. Okay, this will automatically guarantee that no one else can jump and start executing other queries until you finish yours. Okay, that's going to ensure total ordering. Is that clear? Okay. Now if you go back to this example and say why would you not execute them out of order, the simple thing is one of this will be process 1, the other one will be process 2. Okay. One of the replicas is going to get query 1.1 before it gets, let's say, 2.1, or rather 1.2, not 2.1. Okay. So if this one gets 1.1 and then it gets 1.2, it's not going to send an acknowledgement for 1.2, it's going to wait for that process to send an acknowledgement. And in this case, just because 1.2 has arrived, you cannot execute it because you have not gotten an acknowledgement. There's another query in transit, which is why you did not get that acknowledgement. You will wait until that query arrives, you will get the acknowledgement, then process them in that order. So there's no risk of executing them out of order. Okay? So you should go and work this out. Okay? Take a paper and pencil and convince yourself that you cannot have this go wrong because of the way this works. Okay? Once you do a simple numerical example, you will be clear what I'm trying to say. If you're still not clear, come and ask me. Okay? Okay, so we could looked at several different concepts. We looked at logical clocks. Okay? We looked at logical clocks with total ordering. Then we use the total ordering to get totally ordered multicast, third technique. And we looked at vector clocks, which I can actually compare the timestamps. You can do the same thing in vector clocks as well. Okay, this totally ordered multicast works with either Lamport clocks or vector clocks. It doesn't matter. Okay, I showed the example with Lamport's clock, but the same is true of vector clocks. Because vector clocks simply generalize everything that's there in Lamport's clock. So you can use the same technique. Okay, is that clear? Any questions on this? Okay, so we've gone through quite a bit of material. These are important concepts. They're not very easy to understand. You have to actually take a piece of paper and draw some figures and convince yourself how Lamport's clock works, how not logical vector clocks work, what is totally ordered multicasting. There are several more examples in the book. There's also some snippets of code to show you how things work, which may be useful for the lab because you are actually going to implement this in the lab. Okay, so one way or another you got to understand it. Okay, otherwise you can't write code for it. Okay? All right, so we have some time. We are going to continue. Okay, so that's the same thing with vector clocks, which I'm going to ignore. Okay, I already explained everything here. Okay, so I'm going to switch gears and talk about a different technique, okay, which is going to be called distributed snapshots and global state. Okay, so first let me explain the abstract problem. What is it that we are going to address here? Okay, so we are switching gears. We finished clock synchronization. Okay, so this is a slightly different problem. Okay, so essentially the problem is one where we want the ability to run a distributed application. Okay, and let's say there are processes in your distributed application, and let's say there are some failures. Okay, one of the process crashes. Okay, so you're running some application. One process of that n processes crashes. What can you do? Okay, one simple thing is you terminate all of them and restart everything from the beginning. Okay, so you kill all your processes, start up all of them again, and you restart. Okay. Now, let's say these n processes were running some long running job. Let's say they are running a distributed simulation. Maybe you are doing some research, started design jobs, they are doing some computation. And then maybe they have already run for 12 hours. Okay. Now, after 12 hours of computation, one process crashed. You can of course kill all of them and start them from the beginning, but you wasted 12 hours of compute time. Okay. So, question is there a way by which you can not do that? Can you actually keep taking snapshots of the distributed application, so that if there is a crash, you recover from to a later snapshot rather than going all the way to the beginning? Okay. The notion of snapshots is used in operating systems independent of distributed system. So, it is used in things like file systems, it is used in virtual machines, where you take a snapshot and you can restart from that snapshot. Snapshot just gives you the state of that system as it existed at that point in time. Okay, that is why it is called a snapshot. So, you can restart snapshot, it will just continue took the snapshot from that point on. Okay. Snapshots, VM snapshots, and so on. Here we have a distributed application. Okay, we want to essentially try to figure out how do you get a good snapshot. Okay, and to do that, we will define this notion of a global state. Okay. Global state is essentially the state of all of your applications. Okay. You want to essentially capture all of that on disk as part of your snapshot, so you can reconstruct it when you want to. Okay. So, this is a definition. A global state of a distributed system is defined to be the local state of every process, which is the memory contents of every process at some time, okay, as well as all the processes that are in transit. Okay, so, we will take memory contents of every each n processes and all outstanding message, every message that is in transit, that is going to be defined as the state of your application at that time. Okay. So, if you had a centralized process, you know that its state is essentially its memory state. Okay, whatever is in memory is the state of that process at that time. Okay, memory state plus registers, okay, to be more precise. Okay, the same is true here, except that we will also add messages in transit. Okay, so, we will use this for failure recovery, distributed deadlocks, and so on later, but for now we want to understand how is it that you can take a distributed snapshot. Okay, yes, question.
What if it happens such that, so you create the snapshot, somehow say you restore that whatever state, and then you like failed again for the same reason?
Okay, so question is what happens if you fail because you have a bug as opposed to a transient software fault? Now, that could happen. The snapshot won't help you in that case, because the problem is a software bug as opposed to a some OS crash, is not the software application problem. Okay, so you can't figure that out.
Or maybe even if this is actually causing failure, what happens?
Right. So, if you have failures that are caused, I mean, this only helps you recover if there was an error that does not repeat itself. If the error keeps repeating, the snapshot doesn't help, right? So, you can't recover from that kind of error. So, that's something to keep in mind. Okay. Now, the question we are trying to ask is, how do you capture this global state? Okay. Now, a simple technique is if you have perfectly synchronized clocks, every machine is perfectly synchronized with every other machine, ideal conditions. Okay. You will say at noon, all machines will freeze. Okay. They will stop executing. They will take whatever is in their memory, write it out to disk. Okay. They will take whatever is in the socket buffers, which are all messages that are still arriving, write it out to disk, and you you're done. You captured the memory state of every process, you captured every message that's in transit, and you wrote it out. Okay? And that's going to be consistent because all processes are perfectly synchronized. The snapshot at the same time, okay, to be consistent. Okay? That's one way to do it, but you cannot do that in practice because there is no such thing as a synchronized, perfectly synchronized clock. Okay? If you say I'm going to be using a clock synchronization algorithm, I will use NTP to synchronize my clocks, and I'll still do this, it won't work because NTP might have errors. Okay? Typical errors in NTP is 1 to 50 milliseconds. So even if you say let's freeze everything at noon, okay, machines may be off by 50 milliseconds, that's not exactly noon. Okay. So now you have an error because you did not take the snapshot at exactly the same time. You took it at slightly different offsets from one another. Small offsets, but those offsets can matter. The question that we have is, if you do not have a perfectly synchronized clock, how can you still do this in a consistent way? How can you take the snapshot so when I restart my application, things don't go wrong because the snapshots were taken at different times? Okay. So that's what we are going to get from a distributed snapshot algorithm. Okay. So we want what is called a consistent global state, and to understand how this is going to work, I'm going to show two pictures. Okay. So these two pictures are three processes executing, there's exchanging messages and so on. Okay. And the dotted line essentially tells you, okay, when the dotted line crosses a process, that tells you that's the time at which that process wrote its state out, its memory contents out. Okay. So in this case, okay, this process wrote out its memory state at this time here, at that other time there, and still other time there. Okay. The line looks curved because that's clocks. That's how much the clock is out of sync by. Okay. If you had perfectly synchronized clock, this dotted line would be a straight line that intersects them. That's the time at which everyone writes their memory state. Because the clocks are out of sync, they write it out at slightly different times. Okay? And we will see that in some cases that's okay, and in some cases it actually causes trouble. Okay? And we will say this is actually consistent, but that is not consistent. This is called a consistent cut. Cut essentially says where does that dotted line intersect the processes. And we will say this we will allow, this we will not allow. And the reason this we will not allow is you will see that in this consistent, in this cut, you will see that there is a message, okay, and the receipt of the message actually is before this time you took a snapshot, and the send of the message is after that snapshot. Okay. So you will say, what does that matter? Why does it matter where the send and the receive are? The reason it matters is if you restart these processes from this point and that point, what is going to happen is P2 will start executing from that point on. Okay. Once it executes, it will resend message M2 because it's just going to execute all the instructions that it would normally execute. It will resend M2. Okay. M2 has actually been received by P3 process because you are restarting P3 here. Okay. So from the process's perspective, that message is received twice, which is not consistent. Okay, if that message was add $100 to the record account for this user, you are going to do that twice because that first process is going to reissue that query. You will re-execute it. Okay, that's not consistent. Okay, that's one way to think of it. The other way to think of it is basically everything to the left of this cut is past, everything to the right is the future. That's what is to be executed after restart. And you will see that the receipt has actually in the past, the send is in the future, which does not make sense. That's exactly why you actually got an inconsistency. So you got a message that was received before it was sent in the cut. You don't want that. Okay? So you either message, the send and the receive have to all be after the cut. They have to be all before the cut, or we also allow this condition where the send has actually happened, the receipt has not happened. That's okay. You don't want the receipt to be on the other side. Okay. This is why you also have to capture messages in transit. If you simply save the memory state, M3 will disappear because you restart those processes, you did not capture messages in transit. This P1 is not going to resend M3 because it's already sent it. Okay. So you actually have to capture messages in transit and re-deliver them. This is exactly why I said global state is the local state plus messages in transit, because you might have a message like M3 that's in transit. If you don't save it as part of your cut, you're not going to get it back, okay, because it won't be resent. Is that clear what I said? Okay. So that is essentially going to tell us that there are although clocks might be out of sync, okay, if you get a cut that looks like this, you are going to be okay from a consistency perspective. If you get a cut that looks like that, you are not going to be okay, because you will get inconsistency. So you want to see, even though clocks are not synchronized, how can you actually get this and not that? Okay? All right. So we have a few minutes. I'm going to, any questions on this? Yes.
How come the message has to be caught? How come it wouldn't just time out on process 1 and then be resent?
Okay, it's a good question. Question is, why would not P1 time out and get reset? Okay, we do not make any assumptions on what kind of protocols are being used. You can use a UDP message. Okay, UDP has no timeouts. Okay, you just send, and you assume it's going to be received. So if M3 is a UDP message, then it's not going to get time. There's no notion of a time. If it is a TCP message, what you said is right, because it may not have, it may be in transit, maybe you will restore the socket buffers and things like that. But you can't bet on that either, because sometimes the acknowledgement simply means it reached the OS, but not the process. Okay, the ACK doesn't still tell you that, because that you are not, the message has not been received by the process. ACK is simply saying it's received by the machine, not the process. So if you restart the process, though, your sockets will be terminated. Anything in the socket buffers will be deleted. So you still want to capture. Okay, so because we don't make any assumptions, you have to deal with this. That's the short answer. Okay, any other questions on this? Okay, so I'm going to describe a technique which is called a distributed snapshot algorithm. Okay, it's going to work for TCP. I just said that you will send UDP messages and whatnot. This actually only works for TCP, does not work for that UDP example I gave. But be that as it may, the technique is fairly straightforward. But before presenting the technique, I will give you some intuition on what we are trying to do. Okay, you want to capture the state, memory state of every process. You want to capture all the messages that are in transit. Okay, let me give you a real world example of what this means. Okay, so let's assume you are a photographer. Okay, you want to take a picture of the sky. Okay, in a consistent way. Okay, now we'll see what that means. Okay, so assume that there are some birds flying in the sky. Okay, and you also assume that your camera, okay, or your phone camera cannot take the picture of the entire sky in one photograph. Okay, because the field of view is not broad enough. Okay, so to take a picture of the sky, you will have to take multiple pictures and stitch them together. Okay, so that gives you the view of the sky as it occurred, and you want to do this in a consistent way. Okay, so what does that mean? So let's go to the bird example. So if there are n birds flying around, okay, if you stitch all the pictures, there should be n birds in them. Okay. If there's more than n birds, meaning let's say you took a picture here, there's a bird, you move the camera here, the bird again appears in the picture, then you photograph the bird twice. Inconsistent. That's the same as message got delivered twice. Okay? Or vice versa, you are taking a picture here, okay, there's a bird here, it was flying this way, when you move here, it went out of view. So that bird didn't get captured at all. That's like a lost message. Okay? So you want to take your picture and stitch it together, it should represent the sky accurately as it looked. Okay, it won't be exact because you're not seeing this entire snapshot at once, but you captured all the important factors. In this case, it may be things like birds, that you got them in a consistent fashion. Okay? The same thing is true here. You are going to take your memory snapshots are essentially like taking pictures. Okay? These messages are all the messages transit are equivalent to your bird. You want to capture it exactly the way it looked like, but you won't be able to do it once. Okay? Same reason you can't take the picture all at. If you had a wide enough view, you would do it once. Okay? That's the same as saying I have a perfectly synchronized clock, I do this exactly at the same time. That's not feasible. So we want to still do it at slightly different times, yet be consistent. Is that clear? Okay. So this technique takes a little bit of time. We have only 5 minutes left. So rather than do it halfway, I'm going to just stop here today. Okay, we'll continue on Wednesday so I can spend time to describe the whole technique. Okay, so let's stop for the day.